Okay, hi everyone. So today we are going to discuss about fluid mechanics. Now we will be able to review what pressure is. Then we will be discussing liquid pressure, Pascal's principle, and in the second part of the video, we will also be discussing buoyancy and Bernoulli's principle. Okay, so let's start. Okay, now let us recall what pressure is. I want you to look at the illustrations. We have A and B. Which do you think of the two blocks exerts a greater amount of pressure? And then why? Now, if we are going to analyze pressure, if you have two blocks wherein the areas of contact are the same, but the weights are different, so we have different masses, therefore it follows that they have different weights. Now, if they are on the surface, the force exerted by B is greater than the force exerted by A. But the area of contact are the same. So we can now say that B exerts greater pressure because there is greater amount of force. How about this illustration? You have here two masses. We have A and B, but they have the same mass. Okay, so you have here two masses, A and B, but they have the same mass, which is 100 grams. However, if you are going to look at the illustration, they differ in the area of contact. We can say that A has a greater area of contact compared to B. So which do you think exerts a greater amount of pressure? Okay, correct. Letter B exerts higher amount of pressure because the area of contact is smaller compared to A. So we can say that pressure now is directly proportional to the force, but it's inversely proportional to the area of contact on where the force is exerted. Okay, so let's define pressure. Pressure is a force per unit area. Then when a fluid is at rest, it exerts a force perpendicular to any surface in contact with it. And then the force exerted by the fluid is also due to the molecules colliding with its surroundings. So that creates pressure. Okay, so you can see here the different factors affecting pressure, wherein we have force, or the weight of the object, and then the area of contact, or the area of support. Mathematically, we can define pressure as the force over area, or pressure is the ratio of the force to the area over which it is applied. And then if we are going to talk about the unit, the standard unit for force is newtons, and then for area we have meters squared. 1 newton per meter squared is equivalent to 1 Pascal. Now there is this famous demonstration lying down on the bed of nails. Of course, if you stepped on one nail, what do you feel? Okay, you will feel hurt if you step on one nail because of the amount of weight that you have exerted on a very small area, which is the tip of the nail. That is considerably very small. Therefore, the large force over a very small area, that will exert a greater amount of pressure. Unlike when you lie down on the bed of nails, your weight is distributed in a larger amount of area. So that will decrease the amount of pressure that you will feel. Okay, I will attach the link of some demonstration in the description below. Okay, now let's take a look at one application of fluid mechanics. Okay, why is it that a hydraulic lift is able to lift a heavy car while you are just only exerting a small amount of force on this side, but you can lift a car? Okay, so let's discuss Pascal's principle. Okay, so you can see here Blaise Pascal performing the experiment. Now, whatever is the pressure transmitted here, or whatever is the pressure applied here, will be transmitted to this one, up to this, okay, to this area. And the water can actually burst out if you have holes here at the bucket. Pascal's principle tells us that any pressure applied to a confined fluid will be transmitted undiminished to all parts of the fluid. Now let's explain how hydraulic lift works. So whatever the pressure applied at this point will be transferred undiminished to this point, so they have the same pressure. Any change in the pressure of an incompressible fluid is transmitted uniformly in all directions throughout the fluid, and pressure is transferred undiminished. If we are going to analyze here, let's compare the area. The area here is smaller, but the area here is large. So for you to be able to have the same amount of pressure, there should be changes also in the force applied to compensate the change in the area. So let's take a look at the next figure. So you have here a small force, or you have here a small area, so you only have to exert a small amount of force. And that pressure that you have created here, or you have applied here, will be transmitted undiminished up to this point. But the design of the hydraulic lift, it has larger area. Therefore, that small amount of force can be converted to a greater amount of force, that it can even lift a car, just because of changing the area. But you still have to have the same pressure on this side up to this point. Okay, so that is how hydraulic lift works. That's one application of Pascal's principle. Okay, so you have here again the illustration of a hydraulic jack or a hydraulic lift. The area is small, then the force is small, but if you have here greater area, it could also exert a greater amount of force. Okay, that is Pascal's principle. Now, can you think of other applications of Pascal's principle? Now, one application of Pascal's principle also is for syringe. Now, if you are going to observe the syringe, you are exerting force at a larger area, but the needle, the area of the needle, the cross-sectional area of the needle is of course very small. But the pressure you have exerted at the larger area will be transferred undiminished to the needle. So they will have the same pressure. So we have here the total pressure equals the gauge pressure plus the atmospheric pressure. Let's have, for example, the pressure inside the tire. If we will read the pressure inside the tire, that is the gauge pressure. But if we are going to consider the total amount of pressure, we still have to consider the atmospheric pressure exerted on the tire. Okay, so that's the difference between total pressure and then gauge pressure and then also atmospheric pressure. Now, since we are talking about pressure in biophysics, let's also talk about how pressure is measured. Okay, now let's talk about another application of Pascal's principle is the measurement of blood pressure in humans. So you can see here that we have a systolic and then diastolic reading for the blood pressure. Then take note that in measuring blood pressure, the cuff should be at the same level as the heart because the depth affects liquid pressure. Therefore, it also affects the reading of the blood pressure. Okay, let's take a look at the next illustration. So in measuring blood pressure, we squeeze this one so that we exert pressure on this, and then what's inside this is air. So when we squeeze this, air is compressed, and then pressure you created here will be transmitted to the tubes and will be transmitted to the cuff. Then whatever is the pressure exerted on the cuff will then be transmitted to the brachial artery. Okay, so when you do measurement of blood pressure, so you are going to exert the amount of pressure until you reach the maximum output of the heart or the maximum output pressure of the heart. Okay, when that is reached, you could no longer hear any sound. So that is the time when the artery collapses and the flow is cut. So that one that reading that you can see here in the sphygmomanometer, that is the systolic pressure, because that is the maximum output pressure of the heart. And then suddenly, the air will be released. Then you have to note that reading, that is the diastolic pressure. Okay, this is another illustration to explain that. So if the artery collapses, you can't feel it. So there's no pulse, you cannot hear any sound. Then pressure in the cuff above 120, no sounds audible if you reach the maximum output of the heart. And then if the pressure in cuff is below 120, wherein the 120 is the maximum for this example, but above 70, sounds are audible in the stethoscope, and you can feel it. Okay, now when you have the pressure and it's below 70, no sounds is audible until you hear the sound again, and then the blood flow normalizes. So again, systolic is the highest or the maximum pressure, and then diastolic is the lowest or the low pressure. So again, Pascal's principle is applied here because whatever is the pressure you exert while you squeeze the rubber, it will be transmitted to the hose, and then it will be transmitted to the cuff, and then that cuff will also transmit pressure to the brachial artery, and then the pressure of the heart will be transmitted to the cuff, then will then be transmitted to the sphygmomanometer. In that way, we can say that the reading in the sphygmomanometer is really the output pressure of the heart. Okay, for this one, if air is the medium to transfer pressure, the sphygmomanometer doesn't have to be at the same level as the cuff, because the atmospheric pressure will have a minimal effect on the pressure inside the cuff. But if you're going to use a manometer, which is a water manometer, or it makes use of liquids, it has to be at the same level. Just like this one, wherein this one is a way to measure the pressure of the cerebral spinal fluid. So the needle here should be at the same level as the gauge, so that you will have an accurate reading. Okay? So that is about blood pressure and how it's measured, and the application of Pascal's principle. Okay, now let's talk about liquid pressure. If, for example, you have a block of wood submerged underwater, so we can say that pressure is exerted all over it. And then there is also a buoyant force exerted. The force here is described as rho, which is the density of the liquid, the volume of the block of wood, which is area times the height, and then G is the acceleration due to gravity. Okay, this is the amount of force exerted on the block. And then if we talk about liquid pressure is also force over the area. And then you can see here that the force is rho, area times height times acceleration due to gravity, then divided by the area. Then you will have a liquid pressure which is equivalent to rho, which is the density of the liquid, G, the acceleration due to gravity, and H, which is the height or the depth. So that is liquid pressure. The factors affecting it are the density of the fluid, acceleration due to gravity, and then the height or the depth. Now let's also define liquid pressure compared to atmospheric pressure. Okay, liquid pressure is pressure or fluid pressure in liquid which varies with depth due to the weight of the water column above the object submerged. So that is responsible for the liquid pressure. If we talk about atmospheric pressure, that is the weight of the column of air above the surface. But this time, the higher the altitude, the less is the atmospheric pressure. So again, the deeper it is, the greater is the atmospheric pressure. The same with liquid pressure, the deeper it is, the greater is the liquid pressure. For the units of measurement, we have pounds per square inch. We can also use atmosphere. Then we can also use torr, which is a millimeter of mercury. The SI unit for pressure is Pascal, which is equivalent to 1 Newton per meter squared. And then if we are going to convert atmosphere to Pascal, we have here atmospheric pressure at sea level is 1 atmosphere. That is also equivalent to 1.01 times 10 to the 5th Pascal. And then we have another conversion, 760 torr is equivalent to 14.7 pounds per square inch. Okay. Now, after learning about the different factors of liquid pressure, if we are going to compare this one, they are at the same depth, the same liquid, and then the same height. Which do you think exerts a greater liquid pressure? Okay, the answer is none of them exerts greater liquid pressure because they are exerting the same amount of liquid pressure. Since there is the same densities, having the same fluids, and then we also have the same acceleration due to gravity, and then they also have the same depth or the same height. Okay, just like this one, even though they have different shapes, so as long as they have the same depths or the same height, and then the same liquid pressure is applied. Okay, one application of liquid pressure is the intravenous administration of fluids. So you can see here that if there's no height between this and then this one, so that means this cannot flow. Because the pressure will be greater if you have a higher height or a higher depth. Therefore, the pressure at the entrance, here, at the needle, depends on the height of this. Okay, because as we have mentioned, liquid pressure is dependent on the height or the depth. Okay, now let's talk about atmospheric pressure. As we have mentioned, atmospheric pressure is the pressure of the Earth's atmosphere. So this talks about the weight of the column of air. And then 1 atmosphere is equivalent to 1.013 times 10 to the 5 or times 10 to the 5th Pascal. Okay, there is also this demonstration wherein you're going to insert an egg inside a flask or inside an Erlenmeyer flask. I'll give a link of the demonstration in the description box. So how can you fit the egg inside the Erlenmeyer flask? What you have to do is to get a paper, burn that paper, and then put it inside the flask, and then place the egg on top. And then what happens is the egg will now be inserted or will now be dropped inside the Erlenmeyer flask. Why? It's because of the differences in pressure outside the flask and then inside the flask. Where do you think is the lower amount of pressure? Inside or outside? Okay, when you burn the paper and then put it inside the Erlenmeyer flask, you're creating a lower pressure area inside. Therefore, the surrounding pressure is high, and the egg will be pushed from higher pressure area to the low pressure area. And then it will get inserted into the Erlenmeyer flask. Okay, again, take note that the body moves from higher pressure to lower pressure area. Let's take a look at these examples. So if you have here a syringe, and then you wanted to get the water inside the syringe, what you are creating when you pull the piston, what you are creating is a low pressure area. But surrounding it is a higher pressure area. Therefore, the liquid can move from the beaker to the syringe because it's pushed from higher pressure area to lower pressure. Another application is when you drink a straw. Try to drink in a straw with hose. Try to poke holes dito at the end, then using a needle, and then sip the straw. And then you describe how it feels. It will be very difficult to sip in a straw with hose. So because it is very difficult to create a lower pressure area. Okay, and like in this one, when you sip, the velocity of the air is also related to the pressure, which we will discuss in the Bernoulli's principle. But when you sip here, you are creating lower pressure. Therefore, the surrounding pressure here is high, and then the fluid will move from high pressure to lower pressure. Okay, the same thing happens with a dropper. When you press the rubber bulb, you are also creating lower pressure, and then the high pressure area surrounding it will push the fluid into the dropper. Okay. So that is another application. Alright, so now let's talk about another property of water, or property of fluids. You have here surface tension. Now, have you ever thought of why is it that droplets are spherical? Okay, why is it also that there are mosquitoes or there are insects which can float on water or which can walk on water? Okay, that is because of surface tension. The surface tension is the tendency of the liquid surface to contract. That's why it creates this spherical shape because of the attractive forces between the molecules. And then also the surface behaves as elastic film. That is also caused by molecular attractions. But when you add soap on water, you are also changing its surface tension. Okay, I want you to try an experiment. Get water and then pour some pepper on it. Okay, then observe. But now I want you to get a soap. Okay. Dip your finger into a soap, just a small amount of soap, and then place it on top of that water with pepper on it. And I want you to observe what happens. Okay, and then try to explain how that is related with surface tension. I'll wait for your answer for that. Okay, this is one device which can measure surface tension. There's a force exerted and then to stretch the film, and then you have to note the length, okay, or the wetted length. So that will give you the surface tension. So this is surface tension equals force over the length, and then the pressure is equivalent to 4 times the surface tension divided by the radius. Now you can see here the table, in the table, surface tension of some substances. And then you can see water is 0.076. Water at room temperature is 0.072. But if you have a soap solution, you have water at 20 degrees Celsius and then you added soap, it is approximately 0.025. So you can see here, the soapy solution has less surface tension compared to water. Okay, surface tension is also related to the alveoli. So if you can see here, we have the alveolar lining fluid. wherein we have water molecules, and then we have here the air space. Okay, this lining fluid generates surface tension. Okay, this one generates surface tension. But when there is surfactant, that surface tension decreases. Surfactant molecules interpose themselves between water molecules and reduce the surface tension. But why is it necessary to have surfactants? Okay, so let us discuss further the application of surface tension in the alveoli. So you can see in the illustration, if there are no surfactants, so this is composed of water molecules, so there's surface tension here. If there's no surfactants present, the surface tension is high. But if there are surfactants present, the surface tension is lowered. Now, it's analogous to the experiment that you had. Now, when you added soap on water, what happened to the surface tension is that it was lessened. Okay, why is it important that we lessen the surface tension? Lessening the surface tension will allow this one to be flexible. It can expand and then it can contract easily if the surface tension is decreased, unlike if the surface tension is very high. So it will be very difficult to expand the alveoli. Now discussing further, or let us discuss further, why surfactants are very important, or why surface tension should be lessened. Now, I want you to take note of this one also, the Laplace's law, wherein the wall tension is equivalent to the transmural pressure times the radius divided by twice the wall thickness. Or we can also have this expression wherein we have the pressure is equal to the twice the surface tension divided by the radius. Okay. Now, going back to this one, if we can see in the illustration, this has no surfactant. Alveoli 1 and 2 have equal surface tension. However, since this one is smaller, according to the Laplace law, 2 times the tension, it has higher surface tension, or they have the same surface tension. According to Laplace law, they have the same surface tension. However, the radius are different. If we have 2t divided by a small radius, that means there's a higher pressure present in the smaller alveoli. Okay, for this one, since again they have the same surface tension, however, the radius for this one is higher, having higher denominator, that means the value will decrease. So you are going to create a low pressure here. Okay, this now has higher pressure compared to this. And what do we expect? How will the gas move? Take note that objects, gases, fluids, they will always move from higher pressure area to a lower pressure area. So what happens here? This alveoli can collapse because the air can move from this point to this point. Okay? Okay, now let's take a look at the next illustration wherein this time it has surfactant. For this lower radius, it has less surface tension. Okay, that means it has more surfactant per area. If we are going to consider, the surface tension is not lessened linearly by the presence of the surfactants. It also depends on the area or the density. If we are going to look at this, there's smaller radius. Therefore, there is larger density. Because as we know that mass over volume, so if you have a smaller radius, that means you have a smaller volume. So you have a higher density of the surfactants. Therefore, it will decrease the surface tension more than how it's decreased in the larger alveoli. Okay, so if we have here, the addition of surfactants also lessen the surface tension, but not too much less compared to the surface tension here. Because if we are going to consider the density of the surfactants here, the density of the surfactants is considerably lower compared to this. So in that case, what can you say about the pressure? Let us recall the formula for pressure. According to Laplace's law, we have here twice tension divided by the radius. We have mentioned that the tension in the smaller alveoli is considerably less compared to the larger alveoli. So the numerator is less. And then the radius is also small. So you have pressure, an amount of pressure. If we are going to analyze in the larger alveoli, the tension is also small but not very small, but the radius is also large. Therefore, we can now say that they almost have or they have equal pressure, unlike when there's no surfactants present. Okay, 1 and 2 have equal pressure because of the surfactants, and 1 will inflate at a faster rate than 2 until they are equal in size. So this is important to stabilize the size of the alveoli. Okay, why is it very necessary also to stabilize the size of the alveoli? The alveoli is very important for gas exchange. So to maximize that, there should be a greater surface area for gas exchange. Now, looking at this illustration, at this point, this is the case when the smaller alveoli collapses. So there is a less surface area for gas exchange. Unlike when you stabilize the size of the alveoli, there is more surface area for gas exchange. That's why it's very important. Okay, so now let's talk about buoyancy. What is buoyancy and what is buoyant force? Now, when a body is immersed in water, it seems to weigh less than when it is in air. I think you are experiencing that when you're swimming, then you are carrying somebody, then it feels lighter if you are on water. That is because of the buoyant force. So buoyant force is a force exerted by liquid to an object immersed on it. Whenever you immerse an object in a liquid, it will exert a buoyant force. Okay, so why do we have buoyant force? We can relate this one to liquid pressure. We have mentioned that a greater depth, there is a higher pressure or higher liquid pressure, but a shallower one will have lower pressure. If you are going to look at this illustration, on the sides of this cube, or for this material at the sides, they will have the same pressure because they are at the same depth. Therefore, it will just cancel out. But if you're going to look at the pressure at the bottom, and then the pressure on top, the pressure at the bottom is higher compared to the pressure on top. So that one is creating the buoyant force. Okay, and buoyant force is always upward. What are the different factors affecting buoyant force? So we have here the derivation of the formula. We have buoyant force is force 2 minus force 1, wherein we have rho g a h2, that is the area and the height, which is the volume, and then minus the height 1 at a shallower part. Then the area times the height is considered as the volume. Therefore, the buoyant force is rho g. Okay, therefore, the buoyant force is rho gv, where rho is the density of the liquid, not the material, but the density of the liquid. G is the acceleration due to gravity, and V is the volume of the object submerged. Okay, that is buoyant force. Okay, so that is buoyant force. Okay, accordingly, if the weight of the displaced water equals the weight of the object, then it will float. Buoyant force is now equal to the weight of the object. So we can say that the net force is equal to 0. Okay, accordingly, if the weight of the displaced water equals the weight of the object, then it will float. Or we can say that buoyant force is equal to the weight of the object. That means that the summation of forces on the object is equal to 0, or the net force is equal to 0. Therefore, it can float. This is known as the principle of flotation. A floating object displaces a weight of fluid equal to its own weight. And that is also basically the discovery of Archimedes. So we have here Archimedes' principle. The buoyant force acting on the object fully or partially submerged in a fluid is equal to the weight of the fluid displaced by the object. So if you want to get the buoyant force acting on it, you can get the weight of the displaced liquid. Okay, so that is according to Archimedes' principle. With regard to flotation of object floats if the density of the object is of course less than the density of the fluid. And an object is in equilibrium if the net force is zero. I already have mentioned this one earlier. Now also, we can relate this to wearing a floaty. Why is it that you can float when you wear floaty or a salvavidas? Now, what the floaty or the salvavidas is trying to do is to increase your volume. Density is mass over volume. If you increase the volume of the substance by adding air on it without a considerable addition of force or addition of weight, increasing the volume will lessen the density of the object. So that's why wearing a floaty or a salvavidas will make you float, because the volume is increased and the density is lessened. Okay, in fluid dynamics, we also have this Bernoulli's principle. Okay, according to Bernoulli, when the speed of fluid increases, pressure in the fluid decreases. Okay, remember that in your meteorology, if you have higher velocity, that means you have lower pressure. So that's according to Bernoulli. When the speed of the fluid increases, the pressure in that fluid decreases. So there are some demonstration or experiment for this one. I will just give links of those demonstrations. Okay, for Bernoulli's principle to apply, the fluid is assumed to have the following qualities. It should be flowing smoothly. Fluid flows without any swirls or eddies. So if fluid also flows everywhere through the pipe, there's no flow separation, and also fluid has the same density everywhere. It is incompressible like water. So that's when we apply, those are the conditions when we apply Bernoulli's principle. Okay, for the equation, this Bernoulli's principle again is true only for non-viscous fluid flowing at a constant height, and it follows this equation. We have the pressure plus 1/2 density velocity squared plus the density acceleration due to gravity. Y should be constant. If y is a constant, then we can say also that pressure plus 1/2 the density times velocity squared is constant. If that is constant, you can see from the equation, if you can see in the equation here, if you increase velocity, there is a decrease in pressure, so that this value will be constant. Or if you decrease the velocity, you have to increase the pressure, and the value is constant. Okay? So again, take note, if you have faster velocity, that means you will have lower pressure area. Okay, let's discuss some applications. We have, for example, in airplane wing, it's creating a lift, okay, because of the difference in the velocities. Okay, if you can observe here, the wing is curved, and then they will meet at the same point at the same time. Okay, so on the upper portion of the wing, it has to travel a longer distance compared to below it. So the velocity on top is faster compared to the velocity below. So that means also that the pressure on top is lower compared to the pressure below, and there will be a change or a difference in pressure, and it will create a lift, just like the buoyant force. Okay, another application is this. If you're using an umbrella and it's very windy outside, and you're using a curved umbrella, what happens is, para siyang babaligtad yung umbrella. Okay, I think most of you experience that. What happens there is there's also lower pressure on top of the umbrella, because of the faster movement of fluid or faster movement of air on top, and then higher pressure at the bottom. So what happens here? Higher pressure moves to the lower pressure, so the umbrella will move upwards. Okay? Kaya nagbe-bend siya upwards. Okay? So that's another application of Bernoulli's principle. Okay, one practical application also of Bernoulli's principle is if there's a storm. During a storm, it's very windy outside. And then if it's very windy outside, the surrounding of a house has a lower pressure. But inside the house, you have a higher pressure. And take note that objects can move from higher pressure to lower pressure. That's why the roof can be blown upward because there's higher pressure inside the house and lower pressure on top. Therefore, a suggestion or therefore a practical application of this is if there are storms, you have to open the windows, slightly open the windows and open the door so that you are equalizing pressure outside the house and inside the house. Okay, so that's a practical application of physics. Okay, everyone, I think I will end this video